Uh-huh. Good afternoon, everybody, and welcome to episode number 98. We're going to be exploring the Bandwidth Manager, the Cilium Bandwidth Manager today. So we're going to be kind of playing with it, seeing how it works, exploring that functionality. Let's go ahead and get into the news here. Let me present my screen. All right. So our news, as usual, is hosted on HackMD. And if you would like to see, or if you'd like to check out the news, it will be published just like that. So the news can be found at that URL in the lower right-hand corner of the screen down there. It says hackmd.io/echo-live, and you'll find it under episode number 98. There are some upcoming events. eBPF Summit is coming up, and I believe the CFP is still open. I'll be hosting that one with Liz Rice, so I'm really looking forward to that. We have Cilium Con, which will be the second of the really successful events that we hosted at KubeCon in Amsterdam. This time we'll be hosting it in Chicago. CFP still open for that. We just did the first session of Security Summer School, and there are 2 sessions remaining. And so if you want to engage with that, definitely come check it out. The security, the first one that we covered, we did the curriculum of network policies in Cilium Tetragon. And the next one will be transparent encryption and late process execution. And then after that, zero trust and TLS visibility. And if you want to sign up, when you go ahead and click the sign up button, right here at the top, it's important that you select the right time zone. So if you're watching this from Europe, or if you're watching this from America, if you want to come hang out with us and sign up, make sure that you sign up for the correct time zone, because those times are wildly different. Like it's either going to be like 6 p.m. in Europe, probably your time, or it's going to be very early, depending on which one you select. So definitely come hang out, learn a little bit more about Tetragon, learn a little bit more about what we're doing with the security space. It should be a lot of fun. We have some people joining us. Who do we have? Hello, Russell. Good to see you, sir. I'm doing much better. I had a little bit of a cold, but I'm like in that irritating phase of the cold now where it's just a little bit of it left and it's just kind of clinging, but fortunately just a cold. All right, what else do we have? We have talked about Security Summer School. Let's talk about the newsletter. This is a great newsletter. If you have not already signed up for it, definitely do so. You can find it by going to cilium.io/newsletter. And then under the newsletter, you can pop your email address in here, or you could even just look at the newsletters that have already been published. So this most recent is July 11th. And we get into some pretty interesting things. Like Packet, what are you? This was actually a tool written by another engineer here at Isovalent. Hey, Masud, good to see you. Or Masood, I'm sorry, I got that backwards. Good to see you, Masood. PWRU was written by another engineer here at Isovalent who's looking to actually understand how the traffic was moving through things, right? So this is actually from the Cloudflare blog, debugging drop packets from negative header links. And so Cloudflare is actually another user directly of eBPF. And so they're leveraging eBPF to do some of the network functionality here. And in their particular case, they were trying to use, they were trying to determine like where packet drops were happening. And they ended up making use, they were using generic UDP encapsulation. When we make changes to our Kubernetes cluster, we go through several layers of testing. We began to slow rollout. However, large responses had no corresponding latency increase. There was no corresponding increase in latency seen to any requests. Interesting. Through debugging after the incident, we discovered that traffic directors were dropping packets that exceeded the MTU of 1500 bytes, despite the packets being smaller than the actual configured MTU. Interesting. So with the symptoms of the issues identified, dug into it and found PWRU. Filtered on the first column. You can observe some behavior. Originally TCP packet from the load balancer. However, the packet is dropped in the UDP packet destined for the worker's IP on the port. We use GUE. We can surmise that the packet was being processed and encapsulated by IPBS, and form a theory that it was being dropped on the egress path from the director node. We could see also that when the packet was dropped, the packet was still smaller than the calculated MTU. Interesting. So the trace above tells us what kernel functions are entered, but does not tell us if or how the program flow left. This means we don't know which function, k-free skb reason, was called. Fortunately, PWRU can print a stack trace. That's really neat. So in combination with probing, they were able to finally figure out like where the actual problem was. So in some cases, the packets were actually getting to be bigger than this matches their symptoms. So the ultimate fix. At this point, the kernel's behavior was a bit baffling. Why would the tunnel header be computed to be a negative number? To answer this question, we added 2 more probes. The MAC header and the inner MAC header are offsets to the packet layers 2. The network header and inner network header are offsets. Transport header and inner transport header fields are offsets. Oh, nice. That's a pretty clever trick. So basically, because they only had some information, they were actually returning a negative number. So this is a great write-up. I've submitted a Linux kernel patch upstream to fix it. Wow. Nice job. Kind of neat seeing tools that we wrote to kind of help debug some of the eBPF functionality of Cilium used by other companies to help debug their particular scenarios. Pretty neat stuff. So somebody's using eBPF to observe Node.js. How you doing, Bren? Good to see you. And we have B. Elamar. Hello, my first time here. I attended the summer school. Oh, I'm glad you liked it. That's really great. You know, if you do all 3 summer school sessions, then you're going to get a swag box in the mail, which will probably have like stickers and a shirt and that kind of thing. So I hope that you stick to it. Experiments with eBPF. There's a really good example of eBPF of XDP. I actually was just reading through this one. So if you are not familiar with XDP, eBPF and XDP are generally kind of go together. XDP is a way of accelerating traffic, leveraging the NIC itself. Now, what's interesting is that you can also kind of make use of XDP with just generic drivers. You don't actually have to make use of a specific network driver. There is a generic XDP driver as well. So this article gets into like what XDP is and how it works. And so if you're into that kind of stuff, you want to understand like how we can leverage XDP to shortcut particular parts of the TCP stack, definitely check that out. In the ecosystem, lots of good stuff happening. There was just recently a podcast with Liz Rice talking about getting started or learning eBPF. Oh, that's a great image. I like that. Bill Mulligan was doing an Ask Me Anything. From Sidecar to eBPF, an interview again with Liz talking about how we're changing the game for service mesh out there. Discovering the magic of a K-probe. Have fun with K-probe with kernel probing. Really good stuff. Lots of good events coming up. So like I said, we just did the first one and we had BLMR there with us, and we're going to be doing 2 more, both in Europe and also in here in the US. So definitely come check them out. We walk through different labs and show you hands-on like how a bunch of this stuff and functionality works. And for each lab, you actually also get a certificate, which is pretty neat. All right. I think that's the news. Cilium now has 600 contributors, which is pretty awesome. So let's jump into the main topic here. So these are our docs on cilium.io or docs.cilium.io. Boop, close these guys. I don't need them open. So a little bit about what Bandwidth Manager does. And actually let's just talk a little bit about like why it's a thing and why it's interesting. Generally speaking, the architectures of like compute systems over time have changed pretty radically. And we're in a phase now where instead of trying to squeeze out the most performance we can out of every instance of an application, we're creating more of them and horizontally scaling, right? So say, for example, you are a web provider, or you're a Google or a Yahoo.com or whatever, right? And your goal is to serve this web page, this docs page that we're looking at here. A couple of different ways that you could do that, right? You could have one incredibly powerful, incredibly performant web server that is able to serve 10,000 views a second or 100,000 views a second, whatever. Or you could have multiple of them all behind a load balancer, and you're kind of dispersing that work across the whole set. And we're kind of in that phase of that second example where like more and more of the applications we see, I mean, especially if you think about like Kubernetes and stuff, the idea of a deployment is to create multiple replicas of the same application so that you can disperse work across exact replicas of some particular application, right? Whether that be a web server, whether that be some sort of application server, whether that be a function in a larger distributed system stack, and you could have that function be distributed across multiple replicas of the same function, so that you can actually support more load and dynamically support that load with something like auto scaling. But fundamentally, like we're in that phase of computer architecture where instead of thinking about how do we get the most performance out of a single instance, we think about how do we actually scale the number of instances to be able to support the load, which is a pretty interesting time and a pretty interesting state to be in when it comes to computer architecture or compute architecture, application architecture, however you want to describe it. Before that, though, we had actually done quite a lot of work on trying to pull the most performance that we could out of every instance of an application. And this is like, if you look back at network architectures and stuff like that, we started exploring things like QoS. We created much higher performance NICs. We were doing a lot of work to try and figure out how we could get the most performance out of a single instance of an application. And when we think about Bandwidth Manager, we're kind of bringing both of those worlds together a little bit, right? We're kind of doing a little bit of both of those things. Bandwidth Manager here is actually responsible for ensuring that on a given node, you're actually you're reasonably distributing the network bandwidth that is available to that node, to those applications that are hosted upon that node. And so instead of thinking about how much network traffic we can actually get, instead of thinking about like how much performance, instead of thinking about CPU or memory as a constraint for a given node, like how many applications I have deployed to that node or that Kubernetes node, we're thinking in this particular construct about network bandwidth itself, right? I want to think about, say I have 20 web servers deployed to that same node. I haven't dispersed them across multiple nodes, but I want to make sure that the traffic that is landing on that node is not going to impinge the ability for multiple of those applications to be able to use, right? And when you think about it, that particular problem is pretty well known in our infrastructure space because it's a problem that we've all had to face, right? You might remember that, like when thinking about architectures in general, we're always asking questions of like when you're deploying an application into some compute infrastructure, whether that be a virtual machine or a container orchestration system or anything else like that. Some of the questions that your platform team or your the team that you're working with should probably ask, and that you should ask for yourself, are things like, what are the characteristics of this application, right? Is it a fast start application? How much memory does it need? How much CPU does it need? Um, is the application itself CPU bound, meaning that are you going to run out of CPU first, or are you going to run out of memory first, or are you going to run out of network first, right? When you're writing this application, if this application has a bunch of like in-memory uh, data stores, then likely it's going to be a memory-bound application, right? And this also pertains to like how the application itself works. Like perhaps it could also relate to the language that the application is written in, right? So for example, if it's a Java application, generally speaking, with a Java application and a JVM, you consume those resources once at init, and then you make use of those resources during the lifetime of the application, right? And you might do some garbage collecting and those sorts of things. But fundamentally, like the footprint of a Java application is different than, say, the footprint of a Go application or, an application written in Rust, right? These different languages have different characteristics as it relates to the lifetime of an application and that application's consumption of memory, CPU, and network resources. So that's the end of my rant, kind of about like infrastructure and why bandwidth manager is kind of interesting, and it kind of sits together. It sort of acts as a little bit of the best of both worlds, right? You get this distributed mechanism. You can have multiple deployments. You can have multiple replicas. And the problem we're solving with bandwidth manager is how do we ensure that for a given constrained resource, like the network interface into a Kubernetes node, how do we ensure that the consumers of that resource are actually being fair with each other? And what tunables can we put in place that would allow us to kind of ensure that we're not like really, really throttling it? We're not starving one pod and its network bandwidth to feed other pods and their network bandwidth. So there's a little bit of background here on the bandwidth manager, and I want to go through it here. So this guide explains how to configure Cilium's bandwidth manager to optimize TCP and UDP workloads and efficiently rate limit individual pods if needed through the help of earliest departure time EDP, EDT, and eBPF. Cilium's bandwidth manager is also a prerequisite for enabling BBR congestion for control for pods, as outlined below. The bandwidth manager does not rely on CNI chaining and is natively integrated into Cilium instead. That means that for the Cilium will actually configure that leveraging eBPF on the pod's network namespace itself and in the underlying host as well. But it won't make use of a known bandwidth CNI plugin, which is actually part of the CNI project itself, right? So if you have other configurations, like in this example, the example is actually making use of Calico, and this bandwidth plugin is chained after Calico. So when Calico gives a pod a given network, and you wanted to be able to do limitations you wanted to make use of the bandwidth plugin, then you could make use of that and use these annotations, the ingress bandwidth and the egress bandwidth, to limit the bandwidth given to a specific pod. In our case, what we're describing is that we're not using that plugin. We're using eBPF directly. And while we do support the egress bandwidth mechanism, we do not support the ingress bandwidth mechanism. So if you were to configure Kubernetes.io ingress bandwidth, the annotation will be ignored by Cilium's bandwidth manager. Bandwidth Manager requires a kernel of version 5.1.x or more recent, and I have definitely got that. We're going to use Helm to do the install. So let's go ahead and get started here and walk through this process. I'm going to start by doing this on a kind cluster, and if that doesn't work out, then I can create a virtual machine cluster. But first, we're just going to try and do a kind cluster. So first, let's make sure 6.1 kernel, Docker PS should show me nothing. Okay, so kind, create cluster, config. What this will deploy is a kind cluster of 3 nodes with 1 node for a control plane, and it will not deploy a CNI. And the reason for that is because I want to make sure that the CNI is not installed, because I want to install Cilium as a CNI. Can you use both bandwidth at the KH level and bandwidth at the Cilium eBPF layer? If you're into complications. I mean, how would that work? So I guess, so what would happen on the bandwidth side is that bandwidth plugin for the CNI project, it's actually here if you want to look at the code. So CNI project, GitHub. Boop. So the plugin for this is reference plugins. This guy here. So that functionality, code, plugins. I believe the bandwidth plugin is actually making use of it makes use of TC, and it uses the token bucket filter and the QDisk. So generally probably going to be some scalability issues, but like it would be interesting to run them together. I bet you it would actually work. Here's an example of like some of the things that you can do with the bandwidth plugin. Yeah, that'd be interesting. I guess you could do it for ingress, yeah. I don't know that it would conflict because we're writing our stuff in BPF, so we would see and affect traffic on egress faster because we would see it at the kernel layer. On ingress, you would be basically using TC hooks on the underlying host on that interface, so you'd be able to see that traffic on ingress into the host probably a little easier with TC than we'd be able to see it with BPF, because on ingress it has to go through the stack anyway. So I imagine the combination would actually work. It's a good question. We have our cluster stood up here. So I'm actually going to use the Cilium CLI to do this install instead of leveraging the Helm piece of this. And the reason for that is because I have a kind cluster here, and I want to just use all the defaults for a kind cluster, and Cilium CLI will do some discovery of the cluster itself. And so if I do Cilium install Helm set, and I want to bandwidth width manager dot enable to Oh, shoot. No, I did it right. That's what I thought. Kubectl show. I think there's a new flag, Cilium CLI, where it'll actually install it as Helm does rather than as Cilium the CLI does. So kubectl get config map dash n kube system. And what I wanted to see was whether bandwidth manager. So that flag worked. I can see enable bandwidth manager is set to true. Here's all the other flags currently for Cilium configured in this cluster. Did I say that Cilium CLI has some kind awareness presets, or we're just using Helm? Yes, it does. In fact, I'll show that to you real quick because it is actually kind of neat. So, kind create cluster. Big. Cluster real quick. I'll show you what I'm talking about. But you can actually see in the output above here, right? It auto-detected Kubernetes running kind. It auto-detected the cluster's name was kind. It auto-detected that kube proxy replacement was disabled, and then it made a decision to use data path mode tunnel, and it also auto-detected that kube proxy has already been installed, right? And so in this way, I can actually make a bunch of those decisions. It can make a bunch of those decisions for me without me having to make all of those decisions. And Cilium also supports doing something like this, right? So Cilium install dry run Helm values, right? Then it will actually determine, it'll basically look at the same configuration and give you an example of what the Cilium config would look like for that based on its discovery of that cluster, right? So pretty neat. Find delete cluster name equals test. KCTX. So we got our install done. So native host networking devices are auto-detected as native devices which have a default route on the host or have Kubernetes internal or external IP addresses assigned. The internal is preferred over the external if both exist to change manually specifying the devices. I only have the one device in each of my nodes because it's a kind cluster, so it should be simple enough. Verify that Cilium pods have come up correctly. Pods-aw. Looks like everything's running just fine. In order to verify the bandwidth feature has been enabled, do a Cilium status. Kubectl exec ti-n kube system. Cilium status. What? That's interesting. Why does that say disabled? Bum, bum, bum. To verify. So that's interesting. So in our case, we did the install. We saw in the config map that the configuration was set to bandwidth manager true. And we see that bandwidth manager is disabled. Clever. Haha. So this is the problem because I was wondering about this. So this is failing because because we're running in a kind cluster. This is what I was kind of expecting. So I figured I would try it and see what happens. But it turns out that the problem that we're seeing is there's no proc file system in the underlying container. All right, so let's ditch this kind delete cluster. And cd verting. So instead of standing up a kind cluster, we're going to go ahead and stand up a verting cluster, which is a virtual machine based cluster. To do so, we have to do a little bit of work to get everything deployed here. But what this is going to do is stand up a cluster that leverages verting as its hypervisor. And verting, if you haven't seen the last couple of episodes I've done, those last couple episodes talk about a new hypervisor that I've actually just learned about that's written in Rust. It's a VMM. And basically, it operates in a very similar way to the way that Firecracker works. But for our purposes, it creates a cluster of virtual machines running under this new VMM. And we are able to create a full Kubernetes cluster in that way. So let's get this deployed and see if we can actually get a little further with that model. So right now, all we're doing is just kind of standing up the initial internal cluster. And then once we're done with that, we'll go ahead and explore getting Cilium installed. I'm going to mute real quick while I blow my nose. All right. W. Everything to kind of come up here. So this is our cluster API cluster right now at the moment, just kind of spinning up all of the controllers necessary to create this virtual machine environment. Nothing has been deployed yet other than just the actual underlying components themselves. I think we're pretty close, waiting for CAPT system to come online. And almost there. Got it. All right, so that stands up our cluster API cluster. This cluster API cluster is running in kind. I'm not going to spend a bunch of time on this because I've actually done this in the previous 2 episodes, and I don't want to spend a bunch of time on it in this particular episode. It says, Masood says, maybe you want to check your kernel compatibility, your kernel version compatibility here. I think you have it supported, but double checking wouldn't hurt. Yeah, I'm running on a 6 version, a 6.1 kernel, so I know it's supported. I think the problem is that With a kind cluster, the nodes in your kind cluster actually are just running Docker containers. And so the way they mount everything up, it's still just one proc file system. And some of that stuff is hidden from the container itself. So it's not a full rendition of a virtual machine. It's kind of an abbreviated rendition of a virtual machine. So that's, I think, what's causing us the challenge. So in our case, we're actually going to use virtual machines to stand up a cluster instead. So we'll do kubectl apply -f. Interesting. My history going. CDs. There we go. So Pren says, what OS are you on? Fedora user here would be moving to NixOS. I'm actually running Arch Linux. Oh, on Virtink, yes, you're right. But I built my own kernel for it, so it's 5.15.12. So that one will be supported. What else do we have? Can this cluster be built on a macOS M1? Probably not. But I don't actually know the answer to that question. I haven't tried that. It's very possible that you could do it with a bunch of work. I just haven't explored it myself. So I'm going to go ahead and stand up this cluster. We'll see these virtual machines get stood up. Masood says that it could be done. Do you think it would work on an M1? Because, like, basically, I think Cloud Hypervisor would work. Yeah, interesting stuff. I'm running on an Intel machine, so it's a little easier for me. But I don't. I know that M1s have come a long way in their compatibility, but it'd be an interesting one. I know you can stand up kind clusters on an M1. What I'm not sure of is whether you would be able to deploy. Yeah, what I'm not sure of is whether you'd be able to deploy Cloud Hypervisor on an M1. I know that I think I've seen an example of somebody leveraging KubeVirt on an M1, but don't quote me on that one either. I'm not totally sure if that's possible. Okay. Control plane is up. Cloud Hypervisor does or KubeVirt does? Control plane is up. We're waiting for the worker nodes to get started here. They are getting provisioned. All right. Kernel get config C1. We'll put that in the C1 directory, and I'll show you why I do that. I use a tool called direnv, which creates this file called which leverages a file called .envarc, and that .envarc can be directory specific. And inside of there, if I put my export commands, then it will actually set particular environment variables based on a directory that I'm in. So in this case, I wanted to load the kubeconfig when I move into this directory, and when I move back out of it, you can see I'm now talking back to the kindvert cluster, and when I move back into it, I'm now talking to the C1 cluster. So pretty neat. I see the cube, I see the nodes are there, and there's no pods running, so kubectl get pods -aw. Let's do that same command that we did before. Run helm values. Now, this time it's not going to do anything. It's just going to show me the helm values that it determines, and we'll see that it's a different set than what we saw before. Interesting. So in this case, it determined that there was no kube proxy running. I had forgotten that I had turned that off, and that it will install kube proxy on our behalf. It'll leverage the IP address of the service host for that, which is the load balanced IP. So it will do kube proxy replacement. It will use VXLAN as the encapsulation. Yeah, neat stuff. So cat values.yaml. In our example, we're going to go ahead and do the same kubectl. Let's see, get pods-aw. So there is no kube proxy. Yeah. So I think what I want to do is I want to throw that into values.yaml. Let's do Cilium install set equals G. Then we wanted to do and load this. And I think that should be enough to get us there. So let's try that. Waiting for Cilium to deploy here, so it's pulling down the images. And here comes the Cilium agents themselves. Core DNS coming up because now there's a CNI. Cilium operator coming fully all the way up. Haven't seen the Cilium agent settle yet, so maybe there's an issue. We'll see here in a second. Oh, Nope. There we go. They're settling now. Good. Core DNS is also settling. And that same command that we did before. System PS Cilium status. And with manager, hey, it works. Let me get some more water. I'll be right back. All right. So we learned that you can't run bandwidth manager tests on a kind cluster, which is what it is. Give this a little bit longer to settle. There we go. 4.4 reachable. And we have our kind cluster working. Able to see it. Bandwidth manager is configured. We're able to see all of the things work correctly. All right. And we are using kubeproxy replacement strict. And there's no chaining. Everything's healthy. So what's next? So to verify that egress bandwidth limits are indeed being enforced, one can deploy two netperf pods on different nodes, one acting as a server and one acting as a client. What's interesting here is that this is just the two pods. So I don't know why that would deploy two different nodes per se. But let's try it. Like copy vim pods.yaml. If it doesn't deploy correctly for us, then what we'll do is we'll just actually specify the oh, there we go. That's why, because it's anti-affinity. Clever. All right, cool. It'll apply -f pods.yaml. It'll get pods-wide. We can see that it actually did deploy on two different nodes because of the anti-affinity. They are now running. You can also see that the configuration of ensuring that we're leveraging the Kubernetes IPAM was working. So these are the actual networks that the two nodes themselves got. So that's working correctly. So then we want to get the netperf server IP. Copy the first line. So netperf. Is correct. So we got throughput about 9.54. But what if we disabled this value here in the top where it says 10 megabits? I want to disable that and compare the two, right? So if I do delete -f-pod.yaml, I'm going to set the egress bandwidth to nothing. and see what we can actually get. Actually, I'm going to make this a different one. So I'm going to call this metadata name unrestricted. Unrestricted. We will copy yank 17 down. Paste. This will still apply because it's going to throw it onto a different node than any of the nodes that have the term netperf server on them. So go ahead and apply that. Both servers landed on the same node and the client landed on a second node, just like last time. So if we just manually enter the IP of the unrestricted one, what we get? Much faster. And then if we do it to the restricted one, or so without the constraint in place, I was getting more like 1,000 megabytes. And then with the constraint in place, I'm getting 10. Pretty neat stuff. So we can prove that it works. We can prove the bandwidth manager is actually doing its job. Once up and running, the netperf client and netperf server, exactly. So we just go through and we see that everything works the way we expected. And then if we wanted to actually see how that's configured, I actually like this. We can do kubectl exec ti-n kube system via Cilium eBPF bandwidth. So identity 112 will actually be that particular netperf server there. And the egress bandwidth is set to 10 meg. I forget when we actually did the status. Is it configured for BBR? Cubic. To enable Bandwidth Manager with BBR congestion control, deploy the following. Cilium config view. So I'm going to go ahead and enable it using the Cilium CLI. So we'll do Cilium config set enable BBR equals true. In order for, that might actually not work because it's requiring a 518 kernel. And I think I only have a 515 kernel on here. Get nodes -o wide. Yeah, 515.12. Whoops. So for me to make this work, I have to actually upgrade the kernel, which happens sometimes. But let's just see what happens anyway. So kubectl get pods -aw. Yeah, probably complaining about the system Cilium 44. He's a 518 kernel or newer. So Cilium big. All right. So right now we're going to be on cubic because we can't get to BBR unless we upgrade the kernel. The question is, what time is it? It's 11:57 right now. So we've been able to get through the testing. There's actually one more test I wanted to show and actually see if we could actually kind of explore this in a different way. So let's do Cilium. Is it perf? Cilium. Let's see. Activity. Nope. Nope. Hey, look at that. So there's a new network performance test. We could say how long to run it. We could say the duration, the number of samples, etc. So let's just try just running --perf. I just realized that. Oh yeah, good. So let's take a look at the Cilium perf command and see what it shows us. And then maybe what we'll do is we'll modify the configuration of the perf command and see what the result of that would be after the perf is done. So we see something interesting here. In this particular case, we're actually putting the server on the same node as one of the clients, and then another client on a different node. And so we'll have that comparison, I guess, between the two. We're running the test here. I was curious, like, what that would look like from the we can spot the actual device that's passing all this traffic. Probably not because it's running. Okay, so what we got out of that. So then let's see if we can actually change the way this is configured here. So let's do kubectl edit deployment -n Cilium test per server annotations pod.yaml. I want to set this value here. Copy. Yeah. This was set in the template. The perf server will be set to egress bandwidth 10 megabits. All the rest of it should be fine. So the server's been replaced with one setting for that particular value. As our previous outcome is here. Clear. Test. Perf. So I don't think it's going to change the deployment because it's really just validating that the deployment is in a ready state. So the deployment should not, so the perf test shouldn't detect that I've set the annotation to 10 meg. It should just allow me to rerun the same test and see what happens. So what will we see? So describe deployments in Cilium test. Wow, that's interesting. So the TCP stream, perf client TCP stream, 1172. None of these are back down to 10 meg. All of these are more than 10 meg. So interestingly, on egress, unless I'm reading this wrong, it looks like everything didn't see the change. It's the annotation for the pod. is still correct. Wow, that's neat. So we validated it in our other configuration, but when we try to validate it with the perf test command, for some reason that's not applying. So kubectl get pods dash o wide dash n same test. Server's on C1 MD0, so we'll get pods dash n kube system dash o wide grep C1 MD0 HZ. Exec TI system Cilium eBPF and width. Yeah. Cilium. Right. So that's interesting. So we see the 10 meg limit. Maybe these are all under 10 meg. Nope, they're all pretty much over it. Am I setting it in the wrong place? So according to the pods.yaml, limiting egress from the server to 10 meg. Oh, we're also limiting egress on the client. Oh, so let's just go ahead and apply it everywhere. Limit backend same test. Perhaps it was only applying it in the one direction. Test one more time. Let's see if we get a change this time. And should get results here in a second. There we go. So that was our challenge. The clients are actually, I think the one that's egressing traffic, and I wanted to limit that output. So the clients need to be limited to 10 meg, and that's where we saw it because we're only reporting on the clients. So that's the thing. So this actually works. It's kind of an interesting thing, a different interesting use case where you could actually leverage Cilium connectivity test perf to validate the configuration, and it also does the same. Well, that was the last of my tests today. I hope that you learned something. I hope this was educational. I hope that you have a great, great weekend and that you go out there and make the world a better place. And I'll see you all next time. Have a great weekend. I'm going to stop sharing here and I'll see you later. Bye.